So first, I want to, in the first part of the session, specifically discuss some issues on TAT 3.1. So the purpose of TAT 3.1, one of the purposes is to give you a hell of a confusing unit sets to work with. The reason being is that in my experience, when people start really now designing their reactors in next semester, is that it's not the code that bugs them or the principles, applying the principles. It's something silly like a unit system. And when you have a differential equation for dPdW and you've got an incorrect unit, for instance, for your K value, that slope of your dPdW equation may be so huge that you, regardless of which integrator you use, whether you use ODE or solve IVP, it immediately just bombs out because of the irregular, weird slopes that you give. So often the problem is not Python or your understanding of the reactor design theory, but it lies in the units. So please, the purpose of today was to be mean with the units, not that mean. So please note my error that I made in the initial TAT that I published in the units of E. Of course, it must be in joules per mole. What I would like you to take note of is the following. I've had some questions regarding the accuracy, so the accuracy of the answers. So if you think about the conversion, so look at your values for all the answers in that table that I asked. The pressure out the outlet, the conversion, the maximum temperature, remember that's not the outlet temperature, and evaluate them on a whole, right? So there will definitely be some tolerance specifically for in the conversion, but I think the pressure and the temperature values, because their slopes are less sensitive to factors like units or step sizes in the integrators that you use, they should be more closely aligned with the answers that I provide in my table. But X, there's some leeway for a plus minus 1%, I would say, about difference in the conversion when you consider the published answers. So one error that I want to make you aware of, one potential error, is in your dTdW equation, dTdW. So if you inspect this TAT, you will see that delCp of the reaction is not 0. And when I constructed my dTdW equation, I took that into consideration. So you will have your UA term in the correct unit set, and you will have your TU minus T and minus RA divided by stoichiometric number times delH of the reaction, and that needs to be updated to be at the temperature where you are operating at. So in that, after you have now, let me just clear here. So once you have now written your dTdW differential equation, you realize this is going to be a function of delH, which is a function of temperature, and it's also a function of the energy carrying capacity of your flowing streams in the denominator. And that must be updated for each step of your integration procedure in this case. So you cannot, when you in your denominator for your dTdW equation, this is wrong. You can't say FI0 CpI as it was at the inlet to your reactor. So this is incorrect. You must update that. So before, in your function, before you have your differential equation, so you will return your differential equation for dTdW. Remember, you need to calculate delH that you are going to use in that differential equation by saying that it is equal to delH at 298 plus delCp of times temperature minus the 298 reference temperature. And this is the value that gets substituted in there. Also, for your FI CP, once you now have all your FIs for each of the steps, you can calculate that just by having sum of some F's. I will check your questions just now, your comments. FI CP is equal to CPA. Yeah, trouble writing today, plus FbCpB. So this updates and it changes slightly along the length of your reactor because the Cp values do not match the mole masses. Right, so let me just check the comments that you wrote if you've got questions over here. Okay, so 50%, isn't that fairly small? In other words, negligible. Okay, so let me just answer that. And I'm but why is there okay in the more accurate? DP, I had a bit of deviation from the expected answers. Okay, so let's try to first answer Luca's question. What is relatively small and what is relatively large? So if I look at and it all depends. So if I consider my equation for that delH is equal to delH 298 plus delCp T minus the reference temperature. Few things that will affect how sensitive that will be to this variation. So if this is 20 and this temperature relative to my reference temperature is relatively small, so this delta T is relatively small, this starts to fall away. Also, if this is 100,000 and this part of the term is relatively small compared to that reference temperature one, you will see that delH, this becomes pretty much equal to 0 in comparison to that term. So the answer is here, it really all depends on a few factors. It depends on the relative size of this versus the delCp, yes, delCp, but it also depends on how far away am I from my reference temperature. So what is this whole group of terms? And you can evaluate that as for you've got your labs with you in your Python. So you can calculate how this delH varies from that as a function of the temperature and the delCp value. So the answer is it all depends. So this delCp that I gave you for this kind of reaction is actually quite significant. It's quite large. What I would like you to do, if you've completed that, and you achieved the answer, is now see how your answers, how sensitive. So this is a good hint for when you make assumptions when you design. When we make assumptions that make our lives easier, we will always do a sensitivity analysis. Now I must spell it correctly. Sensitivity. There we go. Right, sensitivity analysis on how sensitive is my design decisions on the assumptions that I am making. So you can now always do a reverse sensitivity analysis when you attack this stat, is to say, all right, let me just multiply this term by 0 in my function and evaluate the answers, and then just comment out that FiCp value and just calculate it as Fi naught CPI. And check how sensitive is my answers to this assumption for this specific delCp value. And this is a realistically sized delCp value. It may be even on the bigger size. Okay, so let me just check. There's another chat. How do we decide on what tolerance to use for your design, my design? Okay, so I'm not sure that I understand that question correctly. Our design. Listen, so sensitivity analysis. If you do a sensitivity analysis and you see that if I neglect this, I am going to undersize my reactor by 10%. You would definitely say, all right, it's very sensitive to this assumption. I must either build in a safety factor, or I must do away with my assumption. So that's it. So once you've evaluated this, and unfortunately, I do not have all the answers. It depends on the type of reactor that you design. I suppose at this stage, your questions is more related to your marks and how important is it for your marks, the sensitivity to the answers. Unfortunately, there's a human being, a friendly one, at the other side of marking your tests. So if you feel that, listen, this is just because I use a different integration procedure, or I use a different unit set, and therefore my step size that the integrator chooses, I use dPdW instead of dPdZ. So this is Gareth, this is your answer. If you look at I suggest in your online test, but I strongly suggest that you apply it for your troubleshooting here as well. If you look at the slopes of these two, they will have completely different values. Right, so one may have a big value and this may have a small value, a smaller value, because in this case here you have divided by the bed density and the cross-sectional area. And this step size, or the slope of these differential equations prompts the numerical integrators in Python, so ODE and or solve IVP, to choose their step size differently when they do their numerical integration. So based on that, you may get a different answer whether you use a different unit system, because if you use this in bar, or you use this in kilopascals, or you use this in pascals, you get a different slope over there. And if you have your dFA/dW equation and you write it in terms of kilomoles per second per kilogram or moles per second per kilogram, you must understand that the slope of this one will be 1,000 times less than the slope of that one. And that determines how these integrators decide on its step size. I noticed that some of you, and that's why you get a difference, a small difference in the answers. I noticed that some of you in ODE, in solve IVP, you want to limit that, you want to specify a max step size and tell it, listen, you don't have a choice. And that is, some people do that. I initially also employed that in solve IVP before I started using my dense output function. So if you don't know what I'm talking about, just ignore the subsequent discussion. But if you're aware of this, using this max step size in solve IVP, my suggestion is for our type of differential equations, don't limit Python. So don't tell it you must keep your step sizes small enough, right? Don't limit, let it choose its own step sizes to optimize its integration procedure. Rather, you switch on dense output equals true, and then afterwards generate your smooth curves as I've explained, and I've given some examples in the tats and in the videos. All right, so any questions on that? More questions? Have I answered everyone's questions in the tat? I think yes. So the biggest, using pascals instead of bars for the pressure, actually in your conversion, it's very sensitive to whether you integrate using moles per second per kilogram or kilomoles per second per kilogram. So you can play around with that, but that is the reason why we notice these tolerance differences. I am aware, answer differences within a certain range. I am aware of that, and I definitely take that into consideration when I grade your tests, right? And it's very easy for me to, with a click of a few clicks, to change the tolerances in the test. So when I set up the test, I give an answer value, and then I'm asked for, it must be plus minus, and I have a range of values that I then have in mind that is fair. And if it turns out not to be fair, I adjust that afterwards. So please don't worry about that. What is often, unfortunately, the case is that people feel, oh, my answer is close enough. Especially when we get to that T max values. My answer is close enough, so it's going to be within the tolerances. But what you've neglected is to update your delH reaction with temperature, and that is then an error. And you've neglected to update your FA CpA value, so that will be penalized. So even if the answer is close enough, if you don't specify that, yes, I make this assumption, this is how sensitive it is to that assumption, so that you realize what you are doing wrong, you would have been penalized in this case. Right, a way of troubleshooting that I suggest is, if you have your differential equations, so let me just get something to write with. So if I have defined my DEs, and I've got my independent variable, and I've got my variables, and I've got all my dependent variables, FB, pressure, and temperature. is now equal to my variables. And finally, I return those differential equations, dFA, dFB, dP, and dt. Outside of your function, just run DEs. Ask Python to calculate the value that it would return for that first integration step. So when mass is 0, and give it your initial values. So initial values for your variables, so that it can just return those slopes for you. Often it's then easy if you print the slopes of your equations to spot, if you see nothing is working, to spot a mistake easily. So for instance, if your dPdW, and then you must actually apply a reason to it. So let's say you find that, oh, my dPdW gives me a plus 5,000 pascals per kilogram value. Then you know there's something wrong there. That shouldn't be a plus because the pressure should drop. Or my dTdW returns me a value of 1,000 Kelvin per kilogram catalyst. That doesn't sound realistic. Maybe there's something wrong in my dTdW equation. Or that's an easy way for us to check, and the TAs might ask you to give the initial slope values and the units, and it's then easy to convert those units to kilomoles per second to just see, does the slopes correspond to what we get, and then at least you know in which of your equations must you go and look for an error. And that becomes even more important later on when we have lots of multiple reactions and it's very easy to make a typing mistake or to have a wrong value for K0. So troubleshooting, I suggest employing that to check your initial slope of your differential equations. Okay, questions? Going in the denominator, no, second option, Eric. So in your denominator, always when you have a delH Cp of the reaction that is not equal to 0, in your denominator you will update, so you will leave FA CpA, and you will have to calculate that at each integration step. Right, FbCpP. And the reason being that in your PBR reactor, you're in that slice, the energy carrying capacity changes along the length of your reactor. So you can't use that inlet value because you're interested in what is happening exactly in that slice, and that changes slightly. So we are evaluate, as I suggested, evaluate how sensitive your design is, but it's not that much trouble to update that. So for test exams and designs, if the LCP of the reaction is not 0, update this, update delH reaction in order to get to the answers that I expect you to get. More questions? Anything on TAT 2.2? There's some in TAT 2.2. Let me just say TAT 2.2. TAT 2.2. The volume of that PFR reactor. I think I published an answer of 239 about liters, and I had some students who got 237 about liters. Both correct. Okay, so that is the range of values between 237 and 239.9 about that I would have accepted for correct for that PFR, depending on the integration procedure and the differential equations that you employ. So if you get an answer that is different to the 239, I think 0.6 that I published, around 237, some people got to this 237.2 or 0.4. So let's just say 237 to my answer will be accepted as correct for that 2.2 plug flow reactor in the last part. I think it is in D, where you have to design the optimal reactor train. More questions? Raise a hand if you need some time to type. You don't want to speak. Okay, so I'm going to stop the recording on this part.